Hi, I'm Bob Richards from Washington State University, and today I'll be talking about work we've done on establishing a lower limit on the thermodynamic cost to manufacture heat engines. In this talk, I'll start with the motivation for the work. I'll tell you what our objectives were in undertaking this, and I'll tell you about a model system we've developed involving a crystalline piston cylinder engine enclosing an ideal gas working fluid. We're analyzing that system in terms of a manufacturing operational cycle and looking at the engine lifetime and cost to manufacture coming out of that analysis. I'll give you results on engine lifetime and manufacturing costs and end with some conclusions. The motivation for this work is simple. There's no method to predict costs of manufacture for an engine based on thermodynamic first principles. Up till now, engineers have used empirical methods to estimate costs of manufacture. But thermodynamic methods have been very successful in estimating energy use of engines, and we felt that a similar approach might be useful to find at least limits and functional relationships that control the energy costs of building engines, manufacturing costs of heat engines. So we wanted to identify from a fundamental thermodynamic analysis limits on the cost of manufacture of heat engines. So the question that we're answering is, can a thermodynamic approach put a limit on the cost of manufacture of an engine? It's important to point out here that this is not an effort to make realistic predictions of costs for existing engines. We can't do that. But we can look at a thermodynamic approach to look at functional relationships that control the cost of manufacture and control the limits on that cost. So the model system we're looking at is an ideal gas working fluid enclosed in a piston cylinder made out of a crystalline metal solid. So a monatomic ideal gas working fluid in a piston cylinder fabricated from crystalline metal, and the bonds between the atoms in that crystalline metal piston cylinder are the energy barrier that contain the gas molecules making up the working fluid. So we know that that working fluid, the molecules in that working fluid, will have a distribution of energies, a distribution of kinetic energies. And that distribution will be defined by the Boltzmann distribution. There'll be many molecules or gas atoms that have low kinetic energy and a few atoms that'll have high kinetic energy. The gas molecules in the working fluid will be held in the engine if their kinetic energy is less than the energy required to break the bonds between atoms in the crystalline walls. But if the kinetic energy of some of those atoms is higher than the bond energy holding the atoms together, then that's going to limit the lifetime of the system. So we're going to look at the lifetime of the engine in terms of the bond energy that holds the atoms and the walls together, and the kinetic energy of the working fluid, the gas atoms, defined by the Boltzmann distribution. And if the gas atoms have a kinetic energy higher than the bond energy, those atoms will have sufficient energy to break apart the engine walls. And we know from the Boltzmann distribution that we can predict the number of atoms that will have high enough kinetic energy to break apart the engine walls. So we're going to define the engine lifetime as the length of time before those high kinetic energy working fluid gas atoms break apart the engine walls. And we're going to predict that engine lifetime from the Boltzmann distribution. We're going to take the fabrication energy, the energy required to form those walls, as being equal to the energy of each bond times the number of bonds holding together all the solid atoms in the engine walls. And then we're going to take the cost of manufacture as being that fabrication energy we just talked about, divided by the engine lifetime. And we're adding in or dividing by the engine lifetime because one engine that can last 10 years will be equivalent to 10 engines that can last 1 year. And so if one engine that lasts 10 years takes the same fabrication energy as an engine that lasts 1 year, well, that's really a lower cost of manufacture. So we're going to take this model engine and we're going to analyze it in terms of a cycle, just following the example of Sadie Carnot, who analyzed the efficiency and the energy throughput of an engine in terms of a cycle that the working fluid would undergo, in this case, the Carnot cycle. And Carnot showed that thermal efficiency of that engine undergoing that cycle would be 1 minus the low temperature over the high temperature. So we're going to do the same kind of thing where we're going to look at the engine hardware and analyze it as undergoing a cycle. So in the first part of the cycle, the engine geometry is being defined through manufacture, where we make bonds and form a geometry. Then we put the engine into service, the defined engine into service, and those high kinetic energy atoms in the working fluid are going to start breaking down bonds, breaking down the walls, and undoing the geometry until the engine geometry is broken apart and the engine no longer functions. Once the engine is broken, we can take that solid metal material that made up the engine, we can remanufacture a new engine and put it into service again. So let's look at the manufacturing part of that cycle first. We're going to start at the bottom at step 1, where we've got a portion of solid crystalline material, but the geometry is not defined in the way that we want it. So we're at step 1. What we're going to do is we're going to take that red atom in step 1, and we're going to pull it away from the crystalline solid in step 2, and that's going to take energy, and that's the bond energy EB. And then we're going to move that atom and insert it into this crystalline solid in the geometry that we want, going from 2 to 3, and that's going to define the geometry that we want. You can imagine this process happening from 1 to 2 if we would melt crystalline material, breaking all the bonds, then forming it into a casting, and then cooling it to form the bonds again. The fabrication energy cost is going to be proportional to the bond energy, or the bond energy times the number of bonds that we're breaking. Then engine operation is going to undo that geometry. We're going to have high kinetic energy atoms in the working fluid, and the number of those atoms is going to be defined by the Boltzmann distribution, and those high kinetic energy atoms, gas atoms, are going to break apart crystalline solid atoms. The rate at which those bonds are broken, defined by the Boltzmann distribution, is going to be equal to the exponential of minus the bond energy over kT, where T is the temperature of the working fluid. The engine lifetime is going to be the reciprocal of the rate that bonds are broken, so 1 over ND, and that's going to be the exponential of the bond energy over kT. So engine lifetime is going to be an exponential function of bond energy. So using this analysis, engine lifetime measured in seconds is going to go as the exponential function of bond energy over kT. The cost of manufacture, which we've previously defined as the energy of fabrication over engine lifetime, then will be the energy of fabrication, number of bonds times bond energy, divided by the lifetime, and that's exponential minus bond energy over kT. And we can see here that higher bond energy, if the bond energy of the material we're using for our solid walls is higher, then that will require more energy for fabrication, but will lead to a longer lifetime, L in seconds, and a lower cost of manufacture, C in watts. The results of this analysis can be shown in the two plots here. On the left is engine lifetime in seconds versus working fluid high temperature. And the different colored lines are different bond energies from 0.5 eV to 1.5 eV. And you can see that engine lifetime drops exponentially as we increase temperature and increases exponentially as we increase bond energy, as we saw before. The cost of manufacture on the right, also shown as a function of high temperature and bond energy from 0.25 electron volts down to 1.5 electron volts. And you can see that the cost of manufacture goes up as we increase the temperature of the working fluid because the engine life gets shorter, and it goes down as we increase the bond energy as the lifetime gets longer. So what we've seen here is that we can define an engine lifetime in terms of the length of time before high energy working fluid gas atoms break apart the solid engine walls. This is the most optimistic calculation of engine lifetime. We're not taking into account friction or anything else. This is the longest possible engine lifetime. And so this gives a limit on lifetime. And we can see that it's an exponential function of bond energy and working fluid temperature. Based on this lifetime, we can define an engine cost to manufacture as the fabrication energy divided by engine lifetime. And that's a declining exponential of minus bond energy over kT. And we've shown that that cost of manufacture is extremely small, but all for the shortest engine lifetimes. Thank you very much.